A transpose A, where A has independent columns. So let us see what exactly this is. Independent columns. But then question is, why the hell this A must be independent? The columns of A must be independent. And in order to understand this, we need to go back to this energy again. We need to go back to this energy definition. Because from here, understanding becomes much more clearer. We say if the energy X transpose Sx is greater than 0. Yeah. So let us try to correlate that with this, and let us understand what happens. Okay. So S is equal to A transpose A. So the energy definition is given as X transpose Sx what is S? S is A transpose A. Yeah. And X. Okay. What I'll do here is I'll put a pair of parentheses here. No harm. What does it mean? X transpose A transpose. In matrix, transpose means what? Multiplication of two matrices. Transpose of multiplication of two matrices. What is that? That becomes A X transpose times AX. And what does this mean? This is nothing but a square, right? That's what we write it as norm 2 vector. Long back in one class we studied this. So this is nothing but length squared. Length squared of AX, of vector AX. When this energy, so this is the energy, right? And this is the new form of energy we got. This is the new form of energy we got. So when this energy would be greater than 0, it will be greater than 0 only when AX is not equal to 0. Or we can also say that x is not equal to 0. So if Ax is not a zero vector, and we want to assure that Ax is not equal to 0 or x is um, not equal to 0. I mean, when this is possible, this is possible only when this is possible only when A has independent columns. That's how simple it is. But then one thing for sure here, another definition comes, that is, if at all this becomes 0, negative is not okay, but then uh, this becomes 0, then this is known as semi-definite matrix. So here we have one definition, semi-definite. In semi-definite, you have energy, comma, uh, energy may be equal to 0. You may have the eigenvalues may be 0. If these are the situations that satisfies, we all will also be talking about determinants. Let me write that first. We'll also be talking about pivot. If pivots are 0, then determinant will also be 0. So in this is the scenario where it calls as a semi-definite, but we are more interested for definite matrices. Okay. So this is another test that we saw. Let us look for the another test, one more test. Determinant test. Yeah, determinant test regarding, I've already told you in the last class that it's not just the det, it's not just the determinant of the matrix, rather it is the, yeah, let me write an example, that would be better actually. Let S be 2, 7, 4, 4. Yeah. Whether this is positive definite or not. The very simple test is its determinant is less than 0. 7 to the 14 minus 16 equal to minus 2. So determinant is less than 0. So hence it's not positive definite. Okay. What are the ways I can do it? S. Let me say S1, this one. S2. 2, 4, 4, 8. It's a symmetric matrix again. Now what is S2? This is equal to 0. Semi-definite. S3 is another matrix. 2, 4, 4, 9, let us say. S3. This positive definite. S4. Can you test for this? Well, determinant of S4 is positive. But it says, the definition says that all the leading determinant should be positive. So that is what I wrote in the last class. If I scroll it up and show it to you, yeah, this diagram I made. So determinant of this matrix, the complete one, determinant of this green one, the determinant of this blue guys, determinant of this red guy. Everything should be positive. So here that is lacking in this example that we are talking now. That is what is lacking. Determinant of the first leading guy is lacking. So determinant of this determinant of this is negative. That's a 1 cross 1, but it has to be positive. So let me say, but not all not all leading determinants are greater than 0. Hence, S4 is not positive definite. Okay. Pivot element. Again, we'll talk about the, let us say, pivot element as the test of pivot element. So pivot element, finding pivot element is not new to you. Like in the process of LU factorization, the elimination process, we have already found the pivot elements. The same thing only here. It says that all uh, okay, all pivots of S are positive for a matrix S to be positive definite. So how do I determine the pivot elements? So S is equal to, let us say, 2, 4, 4, 9. Well, we know this is positive definite, but what are the pivot element here? The first one is 2. Yeah, the first pivot is 2. So that is positive. That is for sure. Now in the process of elimination, what you do to make this guy, this 4 guy to be 0? So that is 2 times the first row. Second row is equal to minus 2 times the first row plus second row. That is what we do. So this is equal to 2, 4 remain unchanged. This one becomes 0 and minus 2 times the first row R2 is equal to R2 plus minus 2 times R1. Okay. So This becomes 0. 4 into minus 2 minus 8. 9 minus 8 is equal to 1. So this is our second pivot element, which is also positive. In case of um, well, in case of higher matrices, how will you do it? Higher order matrices. It's all related to the determinant only. It's all related to determinant. And what is the relationship for that? Again, let us take one more example. We'll understand through that example itself. So first thing first, it has to be a symmetric one, and it is symmetric. Yeah. So let us do some row operations. R2 is equal to R2 plus half of R1, and R3 is also same. So how much this becomes? 2 minus 1 minus 1. First element is 0. Second element is 2 minus half, that is 3 by 2. And the third one is minus 1 minus half. So that is also 3 by negative 3 by 2. This is also 0. So this one becomes, yeah, minus 3 by 2. And this one becomes 3 by 2. So we have our leading element. Here this one is our leading element. Here this one is our leading element. And the third leading element we are yet to find. So let us find that one. The third leading element is, what we can do is R3 is equal to R3 plus R2. 2 minus 1 minus 1, 0, 3 by 2 minus 3 by 2, 0, 0, 0. So our third leading element is 0. So this is not a positive definite, rather it's a semi-definite matrix. Okay. So we'll wind up today. That's all we have in today's class. We'll see more in the next class. Yeah.